So here we talk about the magnetic force on the current carrying wire. So at the very beginning of this chapter, we learn about the Lorentz force. Lorentz force is like Fp equals Q times V cross D, something like that. Actually, this is I will say this is another version of the Lorentz force. This is the mechanism itself is actually from the Lorentz force. Okay, so here it says a straight wire carrying a current I in a uniform magnetic field experience a sideway force Fb equals I L cross B. So you can more or less find we have a cross product here and then multiply by another factor. And you can also imagine dq and I has some sort of relationship like I equals dq dt, which is the derivative of the charge with respect to time. So here it says, if you have a wire here fixed at these 2 points, and then the magnetic field is pointing out of the page, and then if there is no current, then there will be no force. If you just ignore the gravitational force, then there will be no magnetic force acting on this wire. However, if you have current going from bottom to top or from top to bottom, then there will be forces acting on the wire here. So here, L is the length of a vector that has magnitude L. So L is the length of the wire, and the direction follows the current. Yeah, the direction follows the direction of the conventional current. So if you have here we have So here the current is going from bottom to top. So now we will consider L is pointing upward, and for this one I is pointing from top to bottom. Then we will assume that L is in the same direction like this. Okay. So of course we have L cross B. L cross B is like L pointing upward, B pointing out of the page. So it is pointing to the right side. It's pointing to the right side. And of course, here we assume that the current is positive because L already follows the direction of the I. So I is positive. So L cross B pointing to the right side, which means that the force pointing to the right side. So this is Fb pointing to the right side. So you can see the wire here bending to the right side. And here, L pointing downward. So L cross B pointing to the left side. And of course, Fb pointing to the left side. Okay, 好似想話你堂啊，所以笑啊。Okay. Okay. So so this is pretty much it. And so if a wire is not straight or field is not uniform, we can imagine the wire broke up into many small straight segments, and the force wire as a whole is then the vector sum of all the forces. So this is something like what we have done in chapter 22. So if it's not a straight line, then we will try to separate into many small segments, and then we deal with each part independently. So which is like dFb equals I dl. So each part is a small dl, and then dl cross b will be times I will be dFb, something like this. Okay, so just now I mentioned that it is similar to the Lorentz force. Actually, I think it is not difficult to know the relationship between them. So let's have a page. So for the Lorentz force, we have Fb equals Q times V cross B. And then here we have Fb equals I L cross B. Okay. So we assume that the current is going in this way, and then yeah. And then the B field is pointing out of the page. B field pointing out of the page. Okay. So so here we can assume that it is positive charge. It is not Hall effect, so we assume it is positive charge is fine here. Okay, so so of course we have some Q going to the bottom, and it is like Q, or we can have D here. Yeah, dq like this. So we have db, dl like this. Okay, so actually we know that I equals dq dt. So we can have a dq over dt here, and then we have v times dt here cross b. Okay. And in that case, dq is actually I, and then v times the dt is the dl, because you consider the charge moving with a velocity v for a small fraction of time. So v times dt will be the length. So this is nothing but dl. This is nothing but dl. This is nothing but I. So actually, this is a kind of Lorentz force. Okay, so here we have a sample problem here. So it says a straight wire horizontal length of a copper wire has a current I through it. What is the magnitude and direction of the minimal magnetic field B needed to suspend the wire? That is to balance the gravitational force on it. The linear density mass per unit length of the wire is 46.6 gram per meter. Okay, here, of course, it will have gravitational force, which is, of course, mg. And suppose there is a current going out of the wire, which means that the L always pointing out of the page. Out of the page, not out of the wire, out of the page. So L, we know L cross B, L pointing out of the page, B pointing right side, so FB pointing upward, right? Using the right hand rule. Okay, so L cross B pointing upward. So if we choose, so here the current I here is fixed. So we need to provide a suitable value of magnetic field so that this FB can be as large as mg. Of course, this B can be very, very small because generally the electromagnetic force is stronger than the gravitational force. Okay, so it will be like FB equals mg. And FB is like ILB. In the vector form, it is like I times L cross B. But here, we assume that B is perpendicular to L. B is perpendicular to L, so it just changed to a simple multiplication, multiplied by 1, something like that. Yeah. So it is like ILB equals mg. Okay, so here we can just move over IL to the right side. We have B equals mg over IL. Or we can have m over L, because here we only have the mass density, which is the mass per length. Mass per length. Okay, so here we have G over I. So this is 46.6 gram per meter. So we need to convert it back to kilogram per meter because kilogram is the SI unit. So we need to multiply it by 10 to minus third power, like this. Okay, so G is 9.8. And then I is 28. So finally, it is 1.6 times 10 to minus 2, minus second power Tesla. Okay, and of course the direction is pointing to the right side. Okay, so this one is simple. Okay, so next we talk about the torque on a current loop. So actually this is the mechanism of the motor or electric generator. 发电机跟那个马达的原理。Okay. So as shown in the figure, right? The net force on the loop is the vector sum of the forces acting on its four sides and come out to be 0. So the net torque acting on the core has a magnitude given by this expression. Okay, so here you can see we have the North Pole on the left side, a big North Pole on the left side, big South Pole on the right side. So between these two magnetic bar, then we will approximate it to be a uniform B field between. Yeah, so the direction will be from the North Pole to the South Pole. Of course, there will be some something like the fringe effect outside, but right between the two poles, then we will assume that the magnetic field is uniform, pointing from left to right. Okay. So here we assume that there is a current for this loop. At this moment, it is like counterclockwise. Counterclockwise. Clockwise is 顺时针. Counterclockwise is 逆时针. Okay, so yeah. So here, if you consider just now the Lorentz force for the current wire, for this side, because you can imagine this is this is L, which is parallel to the B field, so there will be no force acting on it. Similar for this one, there will be no force. There will be no force for these two wires. However, for this one, L is pointing from slightly bottom to top. This is L. And then the B field pointing to the right side. So L cross B will be something like L cross B and then pointing to the bottom. So you see the force pointing to the bottom for the white wire. And for the left wire, the direction of the current is slightly from the top to bottom. Okay, so in that case, L cross B is like L is somehow out of the page, and then L cross B, so pointing upward. Okay, so L cross B is pointing upward. So you can see here F is pointing upward. So in that case, this one pointing upward, this one pointing downward. So it will like this one will be rotating clockwise. So when you see here, the current is going counterclockwise. However, the whole stuff will be rotating clockwise. Okay, if we need to consider in a mathematical way, so n is the number of turn. You may have multiple turn here to increase the torque. So this is n is the capital N is the number of turns. So in these 2 or 3 chapters, we usually use the capital N to stand for the number of turns, and the small n to stand for the number of turn per unit length, which is like the density of the number of turn. Yeah, the number of turn per unit length. Okay, so I is the current. A is the area. A is the area of this coil, the cross-section area. Okay, so B is the B field, the magnitude of the B field. Theta, sine of theta. Sine of theta is the angle between the magnetic field, the B field, and the normal vector of the coil. Normal vector is the vector perpendicular. This is the normal vector. The normal vector is the one perpendicular to this plane. Okay. So here we talk about a concept called the magnetic dipole moment. So in chapter 22, you know what is electric dipole moment. The difference here is that for charge you can have an independent positive charge or independent negative charge. And at that time, if we have a positive charge and a negative charge with the same amount, keeping in a small distance, d, then it is called a electric dipole. However, for magnetic dipole, we cannot have magnetic monopole, as I mentioned before. We can only have magnetic dipole. And for the magnetic dipole itself, we define the physical variable called the moment, the magnetic dipole moment. We usually use mu to specify the magnetic dipole moment here. Magnetic dipole moment. So here it says a coil of area A and N turn carrying a current I in a uniform magnetic field B will experience a torque mu cross B. And here the magnitude of the magnetic dipole moment will be this one. Mu equals N, capital N times IA. So which means that if the current is larger, then the mu is larger. If the area is larger, the mu will also be larger. Of course, with the N, capital N, if you have more turns, then the dipole moment will also be larger. So we have mu equals NIA. So in the previous page, you can see here, this 3 term is actually the mu. So actually it is like tau equals mu B times sine theta. So which is like mu cross B. So mu is the direction. The theta is the angle between the mu and the B field. So here it also tells you that theta is the angle between the the normal vector, and the B field, which means that the direction of the mu is actually the same as the normal vector of the coil. So you can see here, if you have a coil like this, if you have current I here, and this is area A, so the mu will point to this side. So similar question is, we have normal vector either pointing to this side or the other side. Which one is correct? So here we need to use the right hand rule to determine the direction. So you use your forefinger following this. You use your forefinger following this. Ouch. Okay. You use your forefinger following the direction of the current, like this, and then your thumb will pointing to the direction of the normal vector, which is actually the direction of the dipole moment. Okay. Yeah. So this is a magnetic dipole moment, and yeah, the torque will be like mu cross B, and then similarly the potential energy will be negative mu dot B, and then we can also do something like this is the change of the potential energy. The change of the potential energy will be like the work done. If you do some work, you can change the potential energy. Okay, so here, according to this equation, you can see if we have the B field pointing upward, and then your dipole moment also, maybe I can zoom in a bit. Yeah. Okay, so if you have a magnetic dipole moment and also pointing to the same direction, then it has the lowest energy, because you can see the equation is like negative mu dot B. So if they point to the same direction, which means that mu dot B is mu B cosine 0 degree. Cosine 0 degree is 1. Cosine 0 degree is 1, so it is nothing but minus mu B. So it is the smallest number, which means the lowest energy. If this one pointing to the opposite direction, which means that the angle is 180 degrees. So cosine 180 degree is negative 1. So in that case, here you can see negative mu dot B will be negative mu B times cosine 180 degree, which is negative 1. So the two negative signs cancel. So it will be mu B, which will be the largest possible value for this potential energy. Okay. So here we have another sample problem to finish off this chapter. So it says a circular coil with 250 turns, an area of blah blah blah, and a current of 100 MA. The coil is at rest in a uniform magnetic field of a magnitude B, which is magnetic dipole moment initially aligned with B. So in the figure, what is the direction of the current in the coil? Okay, what is the direction of the coil? So it is nothing but something like this. Yeah, it should be something like 3D, although it is like a cross section. So yeah, drawing like this is not so good. Yeah. So something like that. Yeah, because it just follow the right hand rule. Mu pointing to this direction, so the current should be something like that. Something like that. Yeah. Yeah. Okay. So next, how much work would the torque applied by an external agent to have to do on the coil to rotate it 90 degrees from the initial orientation so that mu is perpendicular to B and the coil is again at rest? Okay, so it assumes that it don't have kinetic energy for both situation. Originally it is at rest. After moving it 90 degrees, then it's still at rest. So yeah, so which is like WA equals U of 90 degree minus U of 0 degree. Okay, so which is like minus mu B cosine of 90 degree minus negative mu B cosine of 0 degree. So cosine 90 degree is nothing but 0. And then this is 1. So negative, negative, we have positive mu B. Positive mu B. So which will be nothing but NIAB. So N here is, let's see, N is where? And at the very beginning, 250 turns. 250 turns times I is 100 mu A. 100 mu 10 to the minus 6 power. Okay, so next A is here. 2.52 times 10 to minus 4 times this one, 0.85. So finally it will be 5.36 mu J. Okay, so far any questions?